Okay, ladies and gentlemen, let's go ahead and get rolling here. We got quite a bit to talk about. We're talking about compound transformations. So let's just get into it, shall we? Let me load up my notes here. Okay, so we made a huge discovery today, like a huge kind of breakthrough. And I don't want it to be lost on you how big this breakthrough actually was. We found that we not only can we pretty much, if we know the pre-image and image figure are congruent, that we can get there through a series of transformations, but we can get there through a series of any transformations. Any number in any sequence will get us there. There's literally an infinite number of combinations that will take us from point A to point B, as long as we're sure of two things. Those two things, of course, being that the figures are congruent and that we're only using rotations, translations, and reflections. And of course, everything's drawn to scale if that's what you're given. So let's get into it. Now, certainly you probably want to pause the video if you don't have like the essential question, topic, objective, name, and all that. But that's kind of the beauty of a video. You can pause it anytime you want and rewatch it and rewind it and all that kind of good stuff. So let's jump into it. If we're going to talk about compound transformations and answer the essential question, how can you describe a compound or composite, which means the same thing, by the way, transformation, we probably need to talk about some important terms that are associated. So let's talk about corresponding. So corresponding means, and it means a lot of things. So I'm going to give you a definition of corresponding here, but know that the definition of corresponding I give you is going to kind of morph quite a bit during the course of the year. The definition of corresponding that we're going to use for now is going to be that it maps onto an order. Okay, so here's what I kind of mean by that. It kind of aligns itself really well. We saw an example quite a few times in class, although we didn't really highlight it until just the last couple instances. But if I have this triangle ABC and I say I want to take it onto this triangle or map it onto this triangle DEF, I've actually given you corresponding vertices to map. What I mean is this A, when all is said and done, has to map onto its corresponding vertice DEF. And it's kind of true for all the ones. So B we can say corresponds to, whoa, get out of here, I hate that thing. So we can say that B corresponds to E, and of course now C is going to correspond to F. So when I use the word correspond, I mean it ends up on or maps onto, and the order here does actually matter. So A, B, C corresponds to D, E, F because A goes to D, B goes to E, and of course C goes to F. So if you want kind of more of a picture to go with this, let's say I have this triangle, let's call it ABC, and I want to say map it onto this new triangle, which I'll put in purple. DEF, and of course if we're going to say these things are drawn to scale and congruent, A has to map onto D, which means D can only be put here. B has to map onto E, which means it belongs there, and then C maps onto F, which means it belongs there. So that's what I mean by correspond in order. Through a series, and in this particular case, this is going to be a reflection, of course. Through this reflection, that's where A is going to end up onto D. So a natural thing to talk about in this instance is this term congruent. And the term congruent, and I know we've talked about it quite a bit. No, I'm not going to update iPad right now. Go away. I know we use the term congruent quite a bit in class, but what it really means is exact same structure. Or exactness in structure. In other words, the two shapes, not just in measurement, but are literally the same exact shape. A good example of this would be like if I pick up a stylus, right, and then I pick up another stylus like the ones we used to have in class. Those two are exactly the same thing. Like they're carbon copies, they're stamped copies. In fact, copy is a good word to associate with the term congruence. And we do actually have a symbol, and it's not one we have to use in class yet, but it's important to know that this guy right here, which I'm squaring up in orange, this guy is congruent. It's an equal sign with a little, what we call a tilde on top of it. And we'll see that guy pop up quite a bit over the next month or so in class and its variations. So there we have it. That's going to be our terminology that we'll have to use to talk about compound transformations really well. So let's get out of here. Let's get down to our next question. What has to be shown in order to map a compound transformation? Well, the answer to this question is actually really simple. We have to show everything that we had to show for a single transformation. So the kind of snarky answer is everything we used to show. So we used to have these single transformations like rotations, reflections, and translations. And so we have to show the same thing we used to show for those. But now we have to show it in order. Okay? So in other words, let's say I have this triangle, and let's just call it ABC, and I want to map it onto this triangle here. Now, let me move this guy down a bit. I want to map it onto this triangle, A prime, B prime, C prime. Okay, so every time I make a transformation, so let's say I want to reflect here. Okay, so let's call this like line L, for example, and then point R. I now have to write a description for this. So like this has to come off as a description, which would be like the reflection over line L of triangle ABC that now has to go to triangle RBC. Okay. So that's what I mean by show everything used to show, but now in order. We still have to show the augmented diagram. We still have to show like the description rule, if you will. And then, I should probably change colors. Okay. And then now that I'm doing, say now a second transformation, in this case I'm going to do a translation, I have to do the whole thing again. So again, I have to show the augmented diagram, which I'm doing. Okay. In this case, it's going to be parallel vectors. And then I have to show like the standard rule, so to speak, quote unquote rule. So that description is still going to be like a translation along vector RA prime of triangle RBC, and that will end up at triangle A prime, B prime, C prime. Okay, so it's not a mind-blowing thing. We just have to show order. So if the question is asked, well, what do you have to show? It's still the same things we always used to have to show. We have to show an augmented diagram, and we have to show a description for each step. But now the thing we're going to add is actually we have to show this in order. And this is, of course, one example. We saw some really nice examples, and there are some amazing ones in Edmodo, where people have broken up their work into several different steps, which I think is fantastic. Okay, so now that we know what we have to show, and of course this is just one of those, one example, of course, we have this big question. It's kind of the question we talked about in class. How many series of transformations can map one figure onto its corresponding image? What does this imply? So the answer is actually really simple here. There are infinity combinations. So in other words, if you look at this example, we use a reflection and then a translation. Well, geez, I could have done a translation and then a reflection. So just kind of give you a sense of what I mean, and this is a temporary drawing, please don't draw this. But this is what I had, right? Well, I could have very easily translated to here and then reflected. I also could have translated down here, rotated here, reflected, and then ended back in the same spot. So there are an infinite number of combinations that will take you from point A to point B as long as you're meeting two guidelines. Those two guidelines is that we do have a corresponding image that's congruent and to scale. So what this implies is that any one transformation is really not that important. In other words, if we want a transformation series to manifest itself, we can. It doesn't really matter which it is, as long as, of course, we're describing it really well. So whatever you come up with, someone else can come up with something different, and it's totally cool. Now, the implications of that are vast. It's what we call a generalization, which means as long as I know that they're congruent and to scale, I can always find a series of transformations that maps one onto the other. So And I'm going to go ahead and capture that. So as long as the corresponding figures are congruent, there will always exist a series of transformations that will map them. That's a pretty amazing statement if you think about it. That means no matter what, I can get one spot or one triangle to any other spot, any other triangle. So that's where we are for now. That's our compound transformation. So just like before, if you go ahead and write your summary, and just to remind you, what you have to do to write your summary is to pick 3 or 5 words or phrases that you deem important to answering the essential question. Okay? And then you're going to go ahead and craft that response using the 3 to 5 words or phrases you picked. Okay, so go ahead and write that in your own notes, but just like any other time, if you are willing to take that chance to take your summary and post it onto Edmodo as a reply to this video, I will reward you with extra points on Class Dojo, which translate directly to extra points on your quiz, all right? Because remember, every week the Class Dojo goes down as a quiz, so please make sure that you're doing that. Also, don't be afraid to read other people's. Like, this is a very content-rich area we're creating in Edmodo. Like, there's so much there that you can go to help you, and this is going to become a constant part of our course if you haven't figured it out already. So that's what we have, compound transformations. When you come back on Friday or possibly on Monday, depending on what class you're in, we're now going to take this to the next logical step, which is what if you don't know? What if you don't know that they're congruent and to scale? Because if you look at this statement, and I realize how messy my handwriting is, guys, and I'm sorry, but this says, so as long as the corresponding figures are congruent. But what if you don't know that they are? And that's the question we will tackle next time, all right? So long. Thank you guys for watching this and staying true to what an honors course is about, which is hard work and dedication to the craft. So thank you guys, and I'll see you guys later.